Now we turn our attention to modeling finite state machines. So the first thing that we want to do is look at section 9.2 in the book and look at how we are actually going to do this modeling. So this section it's about leading into how you write the VHDL to do a finite state machine, and it really takes us back to what a finite state machine is and the blocks that are used to create it. Okay? So the best way to learn this is to have a finite state machine example that we can kind of look at and break down and remind ourselves how this works. Okay? So this is really the first finite state machine that you look at in 261, okay? Or I mean in the first 7 modules. And it's a push button window controller. Okay? So this thing right here, let me set it up. Basically, you have a motor that controls a window. Okay? And it's got 2 signals. One of them is CW and one's CCW. It stands for clockwise and counterclockwise. And what you're going to do is if you assert one of the signals, it'll open the window by turning it clockwise. So if you assert CW, it'll turn, the motor will say, oh, you want to open the window, so it spins clockwise. And it'll do it for a certain amount of time and then stop. And then if you assert CCW, it will turn the motor the other way, and it'll turn at a certain amount of time, close the window, and stop. The reason that you need a finite state machine to do this is because if you're going to build a digital circuit that will, every time you press a button to change the state of the window, and that's what we're going to do. We're going to hook up a button, and we're just going to push it. And the window will either open or close. But you need to know whether the window is already open or it's already closed. So you had to have knowledge of what the window was doing in the past before you act. Okay? So that's the simplest finite state machine that you can come up with. You basically have a single input signal, and we'll call it press. Okay? And then the output of your system, your finite state machine, will be these 2 signals, which we call CW and CCW. Okay? All right. In your finite state machine, these are always called synchronous finite state machines. Okay? That means that they are synchronous to a clock. So you will have a clock come in to your signal or to your finite state machine, and whenever you have a clock, you also have a reset. So you have an asynchronous active low reset, and you have a clock. The neat thing about finite state machines is that the clock can run super fast. It could be running at a megahertz. That means that 1,000,000 times a second, it's going to look at the input and take action. That seems silly for something like a window controller, but the point is that most of the time on the edge of the clock, it's not going to do anything. Okay? The only time it's going to do anything is when it sees that button pressed, then it will assert these signals, and then it will go back to waiting for the press. Okay? That's why we're able to have such a fast clock. All right, so the first thing that you do is you take your finite state machine and you break it down into a finite or a state diagram. And this is the classical approach. And we're doing this to remind ourselves how we actually build up these things, because if you always remember how you build the finite state machine, it's easy to code the VHDL. So what we're going to do in this situation is we need 2 states. And the states represent some sort of memory about what's going on in the world that you're trying to interact with. So for example, we can have a state that's called W closed for window closed, and one that's called W open. And depending on where we're at, in that state will tell us whether the window is open or closed. We will take different action depending on what state we're in when press is asserted. Okay, so let's take, for example, that we're in window closed and press is a 0. That means that nobody has pressed a button. All we are going to do is sit in this state. So our next state is we're just going to sit in W closed. We're going to sit there. Next state is nothing more than W closed. In addition to that, we do care about what the outputs are. So when we are sitting and waiting, we will take our 2 output signals, which I actually called open CW and closed CCW to make them more descriptive. Okay? They will both be 0 or unasserted. That means it's not going to mess with the window. If I get a press, I'm going to take this path right here, and when I take that path, it's important to note that I have seen a press. I need to do something to the outputs. But it was based upon not only did I get a press, but I came from this W closed state. If I'm in closed and I get a press, what do I want to do to the window? I want to open it. So the way I do that is I assert the open CW signal, this one right here, and then I keep closed CCW. I don't do anything with it. I keep it deasserted. In addition to those outputs, I move to another state, which is called W open, and that now is where I will sit until I see another input. Okay? The assumption on this state machine is that the press is instantaneous. It's just like a boop, really quick, one clock cycle. Okay? It's not pressed and held forever. It's just, this is a very simple, simplified example in order to get going. Okay. The window has now been opened. We know that it's in an open state because we're in the open state, W open. If I do not get a press, what I'm going to do is just sit in that state, and I will keep the outputs deasserted. So I'm just going to sit here and go, my next state is W open, next state is W open, next state is W open. If I get a press, I'm going to do something different with my outputs. I am this time going to close the window by asserting close CCW. This is the whole magic. Notice that I had a press is equal to 1 in 2 situations, but I knew whether to open or close the window depending on the state I was in. So that was the storage component of the finite state machine. Okay? All right, so that sets the stage for the functionality that we want. Now what we have to do is we have to remind ourselves how you build a finite state machine. Okay. You always build a finite state machine using 3 blocks. Okay? The first block is going to be called state memory. In the state memory, don't know why I went uppercase there. Let's just bring her down. State memory. It's going to hold your current state. That's its whole job. Okay? Its whole job, well, most of its job, is going to hold this thing called current, and I'm going to go underscore state. And I'm going to write these out using the variable names that we'll actually use in our VHDL. Every time you get a clock edge, it is going to update current state with another signal that we call next state. And we'll actually call it next underscore state because then that's a nice variable that I can have in VHDL. When does it update current state with next state? Rising edge of a clock, exactly. So that means that this is where I put the clock that comes into my system, and wherever there's the clock, that means it's driving D flip-flops. Okay? So that means that you have an asynchronous reset that sits down here too. Okay? This is the block diagram for your state memory. It is made up of nothing more than a whole bunch of D flip-flops. So down here, it's nothing more than D flip-flops. So it's got D and Qs, blah, 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 blah. You know what's great about this? Is that at the VHDL level, we don't ever have to worry about how many D flip-flops are in it anymore. Because we are just going to code this up using a process, and we will then say, hey, synthesize as many D flip-flops as you need. So we finally start getting away from the tedious effort of assigning the state codes, making sure we have enough D flip-flops, and wiring them up. Okay, so I have my state memory. Now I ask you this. Who creates the next state codes? Who decides what the next state is going to be? The next state logic. Exactly. So I'm going to write this as the next state logic. And what I'm going to do is I'm going to write it not using a block anymore. I'm going to draw this little like bubble. And whenever in digital logic, whenever you see the bubble, that means combinational logic. Okay? And so this thing right here, don't forget the T, this is going to be called next state logic. Okay? And I ask you this. What does the next state logic circuitry base its decisions on? It is going to produce these codes called next state. But what does it need to look at in order to produce the next state code?
Current state.
Absolutely current state, always and forever. Okay? It will always, always look at current state. So current state is fed back like this into next state. Okay? Next state logic. If you don't look at the current state, you're just a random circuit. Now I ask you, does it look at anything else? The inputs, absolutely. So it has to look at the inputs, which in this example, there's just one bit called press. Okay? All right, so that's really what we do. Does the clock go to that? No. Does the reset go to that? No. Why? Because it's combinational logic. You know why it's so important to break this down right now? Because at this moment we have one block, which is sequential logic. We have one block that's combinational logic. We cannot model those two with one process. We need two separate processes. Let's keep going though before we actually start coding. I'm going to come over here and I now am going to put the third block on here, which is going to be called the output logic. The output logic will produce the outputs. And in this situation, what is the output? There's actually two outputs. Okay, one of them is going to be called open CCW. Let me write it like this. Open CW, and then this is close CCW. And that now is my output logic. What does the output look at? It looks at the current state always. Okay? If it doesn't look at the current state, it's not part of the state machine. It's a separate circuit. Okay? The output logic of a finite state machine always has to look at the current state. It also may optionally look at the input. Okay? Sometimes you look at the input and the current state to produce the outputs. Sometimes you just look at the current state. Okay? In this situation, and that's the difference between the Mealy and the Moore machine, if you remember that term. A Mealy machine looks at the current state to produce the outputs. A Moore looks, and the inputs, and a Moore only looks at the current state. So in this example, you don't even need to know whether it's a Mealy or a Moore. Tell me whether the outputs are based on the input press. Yes. They absolutely are, because you can see that you do it right here. When closed, you come out of closed, press is 1. It's this situation right here where you produce the outputs. So this input press has to also come into here. So I'm going to draw it down here like that. We now have created our logic, or block diagram. Okay, why did I do that? Okay, why did I do that? It's because when we go to implement this thing, we have to think about how we are going to code this up. Number one, we always do a finite state machine using a 3-process model. It is the agreed upon way to create a synthesizable finite state machine. I always start with the current state. Okay? And what I want to do is I don't want to write out the details of the VHDL. What I want to do is I want to look at the process for each one of these blocks, and I want to think about 3 key concepts. If you always think about these 3 key concepts of a process, you'll always be safe. Okay? The first thing we'll do is let's look at the state memory. We are going to model it as a process, and the first thing that I care about is going to be, number 1, who triggers it. This is synthesizable. That means that you absolutely have a sensitivity list. Who triggers the signal assignments in this process? Clock, absolutely. And what else? Reset, absolutely. That is it, never more, never less. This is a sensitivity list for your next state logic, not even close, for your state memory for the rest of time. Okay? That was the first concept to think about. This implies that it's sequential logic. The reason is that we are going to make signal assignments to something else besides what triggers these. The next concept that you have is what are the outputs? Okay? What are the outputs? This process is going to assign to some outputs. You never have multiple processes driving the same signal. Okay? Otherwise you get conflict. So you always think about this process as modeling a group of circuitry which produces outputs. What are the outputs or outputs that this state memory block produces? It's current state, that's it. No more, no less. Current state will be assigned something. Okay? The third concept is this. What are the inputs that you will look at? And I'm going to put like a little squirrely right here, because this is certainly not the logic we're going to use. All we're doing is we're kind of drawing out a process where we think about what triggers it, what are the outputs I'm driving, and what are the inputs. Who do I look at to make the assignment to current state? What are the inputs that I will base my decision on? Next state. Okay? So next state is all that's coming in. So I'm going to look at what next state is, and then I will do that. So next state will be something assigned to current state. There's actually, that's pretty much it. So all this process will really do is every time you get a rising edge of a clock, it'll assign current state gets next state, current state gets next state, except under one other weird situation. It doesn't happen very often. What's another situation that would assign to current state? Reset. Okay? So reset. Those two signals will dictate the values assigned to current state. Okay. So I'm feeling pretty good. Now let's go over and let's look at the next state logic. So the next state logic, you are going to model it with a process. The first thing we want to think about is what triggers the process. Is it combinational logic or sequential logic? It's combinational logic. That means you list every input into the combinational logic that exists. What are the inputs that come into this next state logic? It's going to be press, absolutely, and it's going to be current state. Those are all the inputs that I will base my triggering off of. Okay? Clock reset? No way. They're not getting in here. Those are used for sequential logic. We are building a combinational logic circuit using its own process. Now, the reason that it's important to be its own process is because when I go down and I think about what are the outputs of this process, output or outputs, what are they? Who do I assign to in this process? Next state. So the output of this block, this process, is called next state, and it will get assigned something based upon some logic that you put in here, and that becomes the third thing I care about, which, what are the inputs that I look at? You already listed them in the sensitivity list because it's combinational logic. So you're going to look at press, and you're going to look at current state. Okay, feels pretty good. There's only one more process left, and that is the output logic process. I come to you and I say, we model this using its own process. First thing that I think about is this. What triggers the process? Before we even name the signals, is it combinational logic or sequential logic? It's combinational logic. That means I need to list all of the inputs into the circuit in the sensitivity list. So you say it will trigger off of press? Absolutely. Press came in here, and what else? Current state. Current state, absolutely. So this becomes current state. Life is good. Now we go to the next consideration, which is, what is the output of this? Output or outputs? Well, there's two of them. There's actually open CW. So I'll actually list it kind of like this. So I'm going to do open underscore CW and close CCW. Those are my outputs that I'm going to assign to. The last thing that we consider is what are the inputs? The inputs are easy because it's combinational logic. That means that everybody in the sensitivity list is an input. So that means press and current state. All right. So there we have it. Let's just think about the lessons learned here. Number one, a finite state machine is modeled in VHDL using three separate processes. One process is used to model the state memory. Its sensitivity list has clock and reset, and it assigns to current state. Feel good? The other process is called next state logic. It is a combinational logic process, meaning that we list all the inputs in the sensitivity list. We do not list clock and reset, but we do list current state and any inputs that it looks like. Almost always all the inputs to the system. And it assigns to next state. That's its only output. Finally, we get to the output logic. That's its own process, and it is going to be combinational logic. That means that you always list current state, and depending on the logic, you may or may not list the inputs. In this example, we do absolutely list the input press. And its output is going to be any outputs to the outside world. Three processes, one sequential logic, two combinational logic. And that is the overview of how you model or how you begin developing your VHDL for your finite state machine.